Hi, this is Team SCiO. I'm Andrew Lee,
I'm Nicholas Mladineo.
I'm Shinji Kasai.
and this is our project Mobile Molecular Sensor Control. Next. Okay, so our team was tasked with using an NIR spectrometer called the SCiO device to create machine learning models that could tell the difference between different percentages of anti-strip in asphalt samples, and to be able to develop a mobile app for that to interface with the device. Next. So the way the SCiO device works is basically it's what's called an NIR spectrometer, and it has a sensor on it which measures the reflectivity of light at wavelengths in the NIR region, which is in a subset of the infrared wavelengths, and it's just below human eyesight. Next. So the way it works is it measures the reflectivity of those wavelengths, and then you create collections for samples of these scans, and the SCiO lab is able to basically create machine learning models based on those scans and classify the different samples. Next. So here's an example of a collection that's going over the different percentages of anti-strip in asphalt. And as you can see, each of the different percentages slightly changes how the wavelengths look on the graph. And yeah, next. And here's our application. Has a very simple UI. It lets you log into the SCiO backend, and it'll let you disconnect from the device, get the models from the SCiO backend, take a scan, analyze the scan, and calibrate the device. Next.
Um, asphalt was our experimental sample. We had 10 samples in total, 5 anti-strip M and 5 anti-strip W to test in ambient and without ambient light. Each sample was measured at least 10 times to provide enough data to create a better result for machine learning. Next slide, please. This is the sample results with anti-strip M with ambient light and without ambient light. And you could clearly see that ambient light actually affects the result of the scans. Next, please.
All right, so the previous pictures and whatnot, graphs were all taken from the SCiO website. They have their machine learning algorithms that they run in the back end. So as Andrew mentioned earlier in the presentation, one of our tasks was to kind of come up with our own machine learning algorithms and see if we could do better. The problem is that the company that has this near infrared spectrometer, consumerphycis, they actually have the raw data kind of behind a paywall. It's a $4,000 researcher's license. So we reached out to consumerphycis, and they actually agreed to give us a 3-week trial. During that time, we went and built up all of our scanning sets, and we're able to go through and pull all of the scan data that we did in the lab, and also some of those scans that the previous students have done over the last couple of years. Each scan has 999 data points, and it winds up being 331 each of calibration, raw spectrum data, and reflectivity across the near infrared spectrum. There's a few other data points like time of scan and GPS location as well. So we set out within Python, and we came up with a k-nearest neighbors classifier, and we ran our raw data sets on 3 of the main different types of asphalt that we had done, and actually managed to get an accuracy of 80%. So it was very exciting that we were able to come up with something that had much better than essentially a random guess, which would have been 20% in this instance. And think that we could do a lot more with a lot more scans, and look forward to seeing perhaps what the next next students wind up doing. All right. Thank you for your time.